Okay, so we're looking at a compound consisting of just carbons, hydrogens, oxygens, has a molar mass of 263.3 grams per mole. If a combustion train of that gives 0.1 grams of that compound to give you 0.2 grams of carbon dioxide and 0.0 grams of water, what is the empirical formula? Alright, didn't mean for that to jump up. Right, but what we're going to do is combustion train. We're going to start with that mass of that carbon dioxide, and from it we're going to determine how much carbon was actually in the original sample. So convert that into moles of carbon dioxide using the molecular weight of carbon dioxide, which I can get by 12.01 for the carbon. And oops, I forgot my 1, and 2 times 16 for the oxygen, and we get a molecular weight of 44.01. Alright, we'd have moles. For every 1 CO2 we have just 1 carbon, and 1 mole of carbon has a mass of 12.01 grams. So let's see, I got 0.2014 divided by 44.01 times 1 divided by 1 times 12.01. I have 0.05496. grams of carbon. Alright, I'm going to do the same thing with that grams of water. Going to multiply it by the molecular weight of water. Well, divide it by. Our coefficient here will be different because for every 1 water there are actually 2 hydrogens. This is going to be 1 mole of hydrogen is 1.008 grams. So we have 0.07553 divided by 18.016 times 2 times 1.008. We get 0.008452 grams of hydrogen. Alright, to do a complete elemental analysis and break it down, we'd have to have masses for all of our components, and we have the carbon and the hydrogen, but we don't have the oxygen. What we're going to do to get that is we know the entire sample weighs 0.1. So we will subtract out the part that is carbon. 5,496,96, and we'll also subtract out the part that is hydrogen. 0.008452, and that tells us that there is 0.03. I don't see my marker. There it is. 0.03659 grams of oxygen. Alright. Now, with these values in mind, now we're going to do more like the elemental analysis we've seen before. So the 5,496 grams of carbon, we're going to turn that into moles with the molecular weight of carbon. And we'll do the same thing with the mass of hydrogen, 0.08452 grams. And we will do the same thing with the oxygen. So 0.054 0.96 divided by 12.01 is 0.0045. 004576 moles. 0.00845 divided by 1.008 is still about 0.8. So 0.008385 moles of hydrogen. And the last one, 0.03659 divided by 16 is 0.002287 moles of oxygen. And we'll divide all these by the smallest, which is that 2287. So the 0.0476 divided by the 0.0228 is 2 on the nose, or close enough. The 08 divided by that 0.02002 is 3.66, or what I'm going to write instead is 3 2/3, because that's that 0.66, and this is just 1. And that 2/3 is problematic, so I'm going to end up multiplying all three of these by 3 to give us an empirical formula of C6H, let's see, 3 2/3, 1, 2, 3. Well, heck, I'm going to cheat. That times 3 is 11. And then O is just 3. Giving me an empirical formula, which is what this one asked for. Now, if I wanted the molecular formula, what I do is figure out what this would weigh, and just roughly. It's 12 times 6 for the carbons, plus 16 times 3 for the oxygens, plus 11 for the hydrogens, gives me 131. And if I go back up to the question, I can see that the entire thing weighed 262, so this is about half that. So while this is the empirical formula, the molecular formula, which the problem didn't ask about, but if it had asked for, it's going to be just double all of these. I won't fully box that in because that's not necessarily the answer to this question.